Here we have two graphs, G and H, and we need to decide if they're isomorphic or not. If they are isomorphic, if we think they're isomorphic, then we need to prove it by defining an isomorphism using the function table and edge preservation table. So it's hard to tell right away if these two are isomorphic or not. So one way to do this, what I would personally do is, if you look at G here, you can see there's two degree 1 vertices, A and E. And all the other vertices have degree 2. Notice that that's also true for H. So that doesn't prove that G and H are isomorphic. That just gives me insight into thinking maybe they are. All right, so what I'm going to do is I'm going to unwind G up here. So you think about, okay, taking A, putting it over here on the left, say that's A. And now let's see. A goes to D with an edge, so let's put that there. D goes to G with an edge, put that there. G goes to C, put that there. C goes to H, put that there. H goes to F, put that there. F goes to B, put that there. B goes to E, put that there. Okay, now I think you can see that, in fact, they are isomorphic. G and H are isomorphic. Because we could take H now, and I'll put H right there. Let me stretch H out. Let's see, we've got like so. Well, let's see, let's put X there, then Y, then Z, W, P, Q, U, and V. And now you can see our function that will preserve the edges between G and H. Right, this function will be something like this. Like that. A will go to X, D will go to Y, G to Z, C to W, H to P, F to Q, B to U, and E to V. All right, so let's put that in there. Okay, let's see. We have A going to X, D going to Y, G going to Z, C going to W, H going to P, F going to Q, B going to U, and E going to V. All right, so now let's first write down the edges of G. So let's see, we have an edge AD, an edge, right, we have this edge AD, then this edge DG, DG, then moving on and so on, we've got GC, CH, HF, FB, and BE. And now what is our isomorphism, or we don't know if it's an isomorphism yet. What is our function F from the vertices of G to the vertices of H defined by this table? What does it tell us to do? Oh, that's right, I didn't really verify that it was a function and also a one-to-one and onto function. So before I say function, let me make sure that it is. All right, all of these are different and all the vertices of G are listed there, so we know it's a function. All these are different, so we know it's one-to-one. We've got no D and E's, so it's onto. Okay, so now we know it's a function. So now I can say, what does our function send the edge AD? Well, A goes to X. You can see that right here. And D goes to Y. Okay. And let's see. DG. D goes to Y. G goes to Z. G goes to Z. And C goes to W. C goes to W. H goes to P. H goes to P. F goes to Q. F goes to Q. B goes to U. B goes to U. And E goes to V. Okay, so now let's just check. Are these edges in H? X, Y? Yes, that's an edge. Y, Z? Yes, that's an edge. Z, W? Yes, that's an edge. W, P? Yes. P, Q? Yes. Q, U? Yes. And U, V? Yes. All right, so we've already established that our function, which we're calling f, is one-to-one and onto. It also preserves all of the edges, as established in the edge preservation table with all yeses in the final column. So that tells us that our function f is an isomorphism. If there exists an isomorphism between two graphs, then we say that they're isomorphic. So that tells us that G and H are isomorphic.